Now, the question is, in modern machine learning era, when we think about representation learning, large language models, and reinforcement learning, for example, how exactly we can benefit from the notion of causality and how exactly we can bring causality into those topics. One of those topics is causal representation learning. So in general, representation learning is not a new concept. So if you are not that much familiar with the representation learning, in a high level 20,000 foot view, you can think about it as a process for summarization of your raw features to come up with new features that we usually call latent variables. High level. So there are many technicalities there, and I don't try to butcher the concept, but you can think about it in that way. When we think about causal representation learning, and if you're interested in that topic, I definitely suggest you to go through this paper. It is a nominal paper in the topic by Joshua Benger's group toward causal representation learning. If you think about causal representation learning from distribution perspective, you can think about it in this way, that in statistical models, the aim is to specify a single probability distribution to define the space. In causal models, we care about identifying the effect of interventions. Then it is a matter of trying to see if there are multiple distributions, each one of them related to a specific kind of intervention. For example, as you can see here, intervention for different variables that you have here. In this case, you have 3 variables, and each time we are just changing, perturbing, intervening with one of those, and then we see what is the effect, and then try to come up with a distribution for that. What does it mean? Getting into a little bit more details. The goal of causal representation learning, if you want to define the problem setting, is to learn a representation that tells us about the unknown causal structure. As I said many times, we don't know about the causal structure. Then in causal representation learning, we want to come up with those causal structures. Going back to physics, there's just one specific concept here that is very important, and that's about the sparsity. When we think about rules of physics, for example, we don't have thousands of continuous kind of features affecting different kind of phenomena at the same time. So we have a sparse set of rules that determine a specific phenomena. And it is the same, and those rules are based on the causal roots. In a very high level, like gravity, for example, the electromagnetic rules, we have causal roots behind each phenomena. It is the same in other fields as well. For example, if we get into drug discovery or healthcare, there might be underlying root causes for a specific patients, for example, in breast cancer patients or brain tumor patients, to have worse outcome. We don't expect thousands of genes to have that effect, but definitely because it is a complex disease, there is no one single gene that actually is the root cause. And now the question is, how could we benefit from, for example, causal representation learning, causal discovery algorithms, causal inference algorithms to assess those causal relationships for different purposes? For example, in drug discovery or healthcare, for target identification and biomarker discovery.